So on the last lecture, we left off at this point here. We had talked about uh, space groups and crystal systems. We were talking about the different types of rotations that different crystal systems could have, the number of unique axes that you can have in a crystal system, and so forth. So here we're just going to kind of talk about some key identifiers for the different crystal systems. So if you see a space group, you can quickly identify whether it's going to be, one of the seven different crystal systems. Now for triclinic, there's no really characteristics. It's either going to be P1 or P1 bar. So those are the only two space groups that can be triclinic. There's nothing else. So the thing you're looking for is either does it have just only an inversion center, it's going to be, or excuse me, an identity and the inversion center will be P1 bar. If it's just the identity, which is just a 360-degree rotation, it's P1. So triclinic is either one of two space groups. Now monoclinic, what we're looking for key identifiers is that monoclinic, it has one unique axis. And as we talked about in the last lecture, that unique axis is the B axis. And it's either going to have a twofold rotation, which could be a screw axis or a twofold, and or a mirror plane. And the mirror plane again can be a glide plane as well. So when I mention twofold, I'm including the screw axis with the twofold because it's just translation. And so that's how you know if something is monoclinic. The space group only has one unique axis, and either it's going to have a twofold and a mirror plane, or just a twofold, or just a mirror plane. And so, for example, in these space groups for monoclinic, P2 only has a twofold rotation parallel to the B axis. So the two operators for P2, if I was to write those, let me write them here. So for P2, again, you always have the identity, which is X, Y, and Z, but then you also have a twofold parallel to B. So be negative X, Y, negative Z. So that would be a monoclinic system because A, it only has one axis, and B, the operator is either a twofold, a mirror plane, or both. And so when we get to P2 upon M, this includes a twofold parallel to B and a mirror plane perpendicular to B. So that fits the criteria for monoclinic space groups. Now P21 upon C, a 2 sub 1 is a screw axis rotation followed by a translation. And then we have a glide plane that's perpendicular to the B. So this also is a monoclinic, categorized as a monoclinic space group. So twofold screw axes, mirror plane, glide plane, we use them interchangeably because those are the characteristics we're looking for. Now monoclinic, as we learned earlier in earlier lectures, can either be primitive or C-centered. So you wouldn't see a monoclinic space group that is, for example, in conventional notation, an F-centered or an I-centered space group. It's not common convention to have that centering. So primitive and C-centering are the only two space centerings that monoclinic can have. Now to show you the difference between C2, and we'll do more of this in part 2, but just to give you an idea. So to show you the difference between C2 and P2, again, P2 is primitive with a twofold rotation. We wrote those symmetry operators here. Now I want to show you the difference between P2 and C2. Now remember, since it's C-centered, it's going to have two lattice points. So each lattice point gets its own set of symmetry operators. So if I was to write the symmetry operators for C2, it would be double the symmetry operators for P2, because the reason it's doubled is because it has two unique lattice points, because it's the primitive lattice point plus the C-centered lattice point. So just to show you what C2 would look like. So again, we would still have the same operators as P2, so we can go ahead and write those. Now, in addition to that, we'll have two more. So you have the identity X, Y, and Z. For C-centered, you would also have the C-centered identity, which would be X plus, or I should write it as 0.5 plus X, 0.5 plus Y, Z. So the difference between 1 and 3, 1 is the identity for a primitive lattice point. 3 is the identity of a C-centered lattice point. And then for the fourth symmetry operator would be a twofold that's been shifted, that's been C-centered. So if we look here, we get 0.5 minus X, 0.5 plus Y, negative Z. And so the difference between primitive and C-centered is you have double the number of symmetry operators, because for C-centered you have a total of 2 lattice points versus primitive that only has 1 lattice point. So that's the difference between something that is primitive and something that is axial centered, so centered along one of the axes. So for example, P2 upon M, which is shown here, is primitive. It has 4 symmetry operators. C2 upon M would have 8 symmetry operators because it's C-centered. It's going to have 2 lattice points. So what you could do is, if you know all the symmetry operators for the primitive form, you just multiply by the number of lattice points that you have to generate all of the symmetry operators. Now, that's monoclinic. Again, one unique axis, which is the B-axis, so everything revolves around the B-axis in monoclinic, and you're either going to have twofold rotations, screw axes, or a mirror plane, or a glide plane. So you can have a combination of both of these, or just one of them. That's characteristic of monoclinic. Now we move on to orthorhombic. Orthorhombic has 3 unique axes. And these are going to be the A, B, and C axis. And orthorhombic is always going to have 3 operators present. And this is present in the space group. So anytime you look at a space group for orthorhombic, it's always going to have 3 operators listed in the space group. Now these can be a combination of, again, twofolds. And again, I also mean screw axes as well, twofold rotations and or mirror planes. So very similar to monoclinic, except now instead of just one axis, we have it over all 3 axes. And that should be mirror planes, not mirror. Yeah. But with orthorhombic, we can have a variety of different centerings. We can have primitive, C. In addition to C, you don't be surprised, you see A and B as well. And we have body centering and face centering. So orthorhombic has a variety of different centering options. Now, you may say, well, orthorhombic has primitive side centering, or excuse me, axial centering, body centering, and face centering. How can we tell the difference between orthorhombic and cubic? And the way you can do that is orthorhombic will only have twofold symmetry. So if you look, for example, orthorhombic, P21, 21, 21, all twofold. Whereas for cubic, generally one of the symmetry operators is a threefold symmetry element. So if you see a threefold symmetry element in a space group, automatically you know it can't be orthorhombic. Orthorhombic can either have two folds / screw axes, a 2-to-1 screw axis, or mirror planes / glide planes. If you see a threefold, fourfold, or even 6-fold symmetry in the space group, definitely not going to be orthorhombic. You can only have twofold symmetry, and mirror planes. That's it. So just like with C-centering, if we look at P and MA, it's primitive. And I'm not going to write all these out because as you go to higher symmetry, you get more operators. But just to show you a comparison, PNMA has 4 symmetry operators. Now, if we went to something that was C-centered, for example, CMC2 sub 1, every primitive, and this is important here, every primitive orthorhombic space group has 4 symmetry operators. So if it's a primitive orthorhombic, you're going to have, oh, no, I shouldn't say that. That's not right. We'll get to this. This is talking about centrosymmetric and non. We'll get to that in just a second. So yeah, scratch that from the record. We'll talk about that in just a second. So the reason is for orthorhombic, if it's centrosymmetric, orthorhombic is going to have possibly 8 operators. If it's non-centrosymmetric, it's going to have 4 operators. And we'll talk about that in just a moment. But the key thing for orthorhombic is 3 unique axes and either has a 2-fold symmetry or mirror plane symmetry. Now getting to tetragonal, if you remember, tetragonal can have up to 3 unique axes. Now the main axis is the C-axis. So when I say can have up to 3 unique axes, it doesn't mean that you're always going to have 3 operators in the space group symbol. It means it could have up to 3 operators, but you will always have 1 operator, which would be the C-axis. And the characteristic of tetragonal is you always have 4-fold symmetry as the first principal symmetry operator. So 4-fold symmetry is always present in tetragonal, and as you can see from the examples, is typically the first operator listed for all tetragonal space groups. So you're always going to see the 4-fold symmetry in it. Now, as far as centering, tetragonal can either be primitive or eye-centered space groups. So we can have primitive or body-centered space groups. Now, the way you can tell the difference between tetragonal and cubic, because if you notice cubic has some 4-fold symmetry, is you got to look at first the centering. So if you see a space group such as F432, well, you'll notice this is F-centered, and tetragonal cannot be F-centered, even though there's 4-fold symmetry present. But if we were comparing, say, I41 4 sub 132, now I is body-centered, but tetragonal cannot have 3-fold symmetry. So tetragonal can only have 4-fold symmetry, and a minor symmetry could be 2-fold, but it cannot have 3-fold symmetry. So if you see a body-centered space group with 3-fold symmetry, it cannot be tetragonal. Tetragonal has to have 4-fold symmetry as the main symmetry operator, and it can have additional rotational symmetry, but that's only 2-fold. Can't have 3-fold for tetragonal. Now, primitive, we said has 1 lattice point. So if it was body-centered has 2 lattice points. And so what that means is that the number of symmetry operators for a body-centered compared to a primitive would be double. So if you know all the primitive symmetry operators, and you have this exact same space group, but now it's body centered, it's going to have double the number of symmetry operators. Because again, for body centered, you have 2 unique lattice points, and each unique lattice point gets its own set of symmetry operators. So now moving to triagonal, and triagonal includes rhombohedral as well. So these go hand in hand. Now trigonal has to have threefold symmetry. And so that's the main operator in trigonal. This is the main one. It has to have threefold symmetry. So if you look here, we have a threefold roto inversion, a 2 screw axis, a threefold rotation. So trigonal, even rhombohedral, the key is, and I'll just put /r so you know it's for rhombohedral, the key is it has to have, as one of the primary symmetry operators, a threefold rotation as a roto inversion, a screw axis, or just a plain rotation. Now, rhombohedral, the easiest way to know if something is rhombohedral is it's going to be R-centered. So if you see something with R-centered, it's going to be rhombohedral. Nothing else has R-centered. But if you see it's primitive with on the main axis, a threefold rotation, it's going to be trigonal. And you may ask, how would I determine the difference between trigonal and cubic? Well, for one, on the main axis, it should be a threefold rotation. So if you look at cubic, the ones with threefold rotation don't have the threefold on the main axis. Secondly, trigonal can only be primitive. So for example, Fm negative 3m cannot be trigonal because it's face centered. So again, trigonal only can be primitive centering, and on the main axis has to have some type of threefold symmetry. And again, the main axis is the first one always listed in the symmetry operators. So trigonal is primitive centering. Hexagonal, this is very easy. Hexagonal, it's going to have some type of 6-fold symmetry operator. Now this could be a screw axis, it could be a roto inversion, or it could be a regular 6-fold rotation. But that's the characteristic of hexagonal. If you see 6 in the space group, automatically you should know it's hexagonal. No question about it. And for hexagonal, there can only be primitive center. So hexagonal, tetragonal, they're very easy ones to recognize because they have the characteristic for tetragonal 4-fold symmetry on the main axis and hexagonal 6-fold symmetry on the main axis. And even trigonal is going to have the characteristic 3-fold symmetry on the main axis. Now we get to cubic. And so cubic, the best way to understand cubic is if it doesn't fit any of the other ones, then it must be cubic, because cubic can have primitive centering, body centering, and face centering. But notice it cannot have axial centering. So the way, and probably the most difficult one, is to distinguish between cubic and orthorhombic. Well, one thing about orthorhombic is it can have axial centering. So it can have a C-centered, an A-centered, or B-centered unit cell. So that's one way you can distinguish between cubic and orthorhombic. As for cubic and the rest, tetragonal, trigonal, and hexagonal, we've talked about the characteristics distinguishing between those. But another thing to help distinguish cubic from orthorhombic is that cubic may have additional rotational symmetry that's not twofold. So you may see a fourfold or a threefold rotation. Those are types of rotation that orthorhombic can't have. Orthorhombic can only have twofold rotation. And you'll notice with cubic, again, you have multiple types of rotational symmetry. Whereas in tetragonal, trigonal, hexagonal, usually it's one type of symmetry. So for example, P23 has twofold and threefold symmetry. Well, that's the only crystal system that can have twofold and threefold symmetry in the primitive form, where you'll notice again that the twofold is on the primary axis. So if you look at P223 is cubic, R32 is trigonal. Again, the threefold is the first symmetry operator on the primary axis in trigonal. In cubic, for P23, it's not. It's on the secondary axis. So therefore, it would be cubic. Again, PN3M, the roto inversion is not on the primary axis. Whereas for trigonal, you'll see P-3-1M, the roto inversion is on the primary axis. Now, when you get to things with fourfold rotation, for example, this one, it's F-centered. Well, tetragonal cannot be F-centered, so therefore it has to be cubic. If it's body-centered, like we talked about, tetragonal can only have fourfold rotation and could have twofold as well. So here we see a threefold rotation. It cannot be tetragonal. So these are some key identifiers to help you identify what type of crystal system it is. And if you can go through and know it's not monoclinic, orthorhombic, tetragonal, trigonal, or hexagonal, then by default, it would have to be cubic. Now, one thing just to mention is, we said primitive is one lattice point, body-centered is two lattice points, but face-centered is 4 lattice points. So what that means is when you determine the number of lattice points at the primitive lattice point, you would have to multiply those symmetry elements by 4 to get the total number of symmetry elements. So face-centered space groups can have a very long list of symmetry elements in it. So those are the key identifiers. Now let's look at some other stuff involving centrosymmetric, non-centrosymmetric space groups. So what I want to show you here is, out of all the 230 space groups, only 5 are found in about the majority of organic structures. So organic crystals, organic and organometallic, I should say 85%, roughly. It's not a hard number, but about 85% of organic, organometallic structures fall within 5 crystal systems, or space groups, I should say. So out of all the space groups, we have 230 space groups. Out of all of them, the majority of organic and organometallic structures fall within just 5 space groups. And these space groups are, and this is important to note, these space groups are P1 bar, P21, they're all the ones shaded in red, P21 upon C, C2 upon C, P21, 21, 21, and PBCA. So out of all 230, these are the main 5 that about 85% of organic / organometallic structures fall within. And I have seen these space groups pop up numerous times when solving crystal structures. So you can see these are only contained in about 3 crystal systems: triclinic, monoclinic, orthorhombic. Now these are just the majority of the ones, but we do have some other crystal structures that fall into other groups, but these are the most common space groups. So if you had an organic or organometallic structure, you know, 8 times out of 10, or 8.5 times out of 10, it's always going to fall in one of these 5 space groups. So now what we're going to talk about is how can we identify centrosymmetric and non-centrosymmetric space groups by sight. So just by looking at a space group, can we identify if it's centrosymmetric or non-centrosymmetric? And both of them have different types of properties. So again, centrosymmetric means it has an inversion center somewhere in that list of symmetry elements. So rather than having to go through and generate every symmetry element, is there a quick way, hey, I can look at the space group and bada bing, I know it's centrosymmetric or non-centrosymmetric. So here are some key observations to make sure you look for in a space group to see if it's generating inversion centers. So we'll go through these. The first one is a mirror operation perpendicular to a rotational axis. So what this means is, do you have a rotation, say a twofold parallel to B, followed by a mirror plane perpendicular to B? So if you have a twofold on a particular axis, and then you do a mirror plane along that axis, perpendicular to the axis, excuse me, that's going to generate an inversion center. And we'll see that in just a second. And the way these are written in space groups is like this: 2 upon m. So when you see something written like this, or 4 upon m, or 4 upon c, 2 upon c, or 2 sub 1 upon c, that's when it says it's a mirror plane perpendicular to a rotational axis. And this does produce a inversion center. Now what about if we have 3 perpendicular mirror planes? So for example, if we have a mirror plane perpendicular to A, and then we do a mirror plane perpendicular to B, and then with that we do a mirror plane perpendicular to C, what we're going to generate is an inversion center. So when you have 3 perpendicular mirror planes, we're going to generate an inversion center. Now these can be mirror planes and or glide planes. If they're glide planes, the inversion center will not be on the origin. If they're all mirror planes, then the inversion center will be on the origin. So whether it's a glide plane or a mirror plane, as long as you have 3 perpendicular mirror/glide planes, you're going to have an inversion center. So you automatically know they're centrosymmetric. So to give you a few examples of space groups, for example, if you had PMMM, which is orthorhombic, you have 3 perpendicular mirror planes. Or if you had PBCA, you have 3 perpendicular mirror planes. They're going to have inversion centers. Now the difference between PMMM is that its inversion center is going to be on the origin versus PBCA, where its inversion center is going to be shifted off the origin. Now if you have a combination of mirror planes and glide planes, it's still going to give you an inversion center. However, when you have a combination of both, it's going to shift it off the origin. And I might show you an example of that here in just a moment. Now, what about, does the same hold true if we have 3 perpendicular rotational axes? So if we take a twofold parallel to A, and then a twofold parallel to B, and a twofold parallel to C, can we generate an inversion center? And if we look at the bottom, the answer is no. So if you have 3 perpendicular rotational axes, they do not generate an inversion center. So an example of this space group would be something like P21, 21, 21, or let's see, I think one is like C22. These would not have an inversion center. So AKA, it would be what we call non-centrosymmetric. So 3 perpendicular rotational axes do not generate inversion centers. Now, if we look at an odd roto inversion, so an odd roto inversion is like a threefold roto inversion, and an even roto inversion is a fourfold or sixfold. So these are the only types of roto inversions we can have. You can have a threefold, which is odd, and you can have a fourfold or sixfold, which is even. Now, I don't know if you remember this, but we did touch on this when we were talking about symmetry elements. We discussed roto inversions. We said that odd roto inversions can have an inversion center. So if you see an odd roto inversion, automatically you know it has an inversion center listed. If it has an even roto inversion, it does not have a inversion center. And if you go back to our notes on symmetry, it explains why odd does and even doesn't. So odd roto inversions, automatically they're going to be centrosymmetric. Even roto inversions, no inversion center is going to be non-centrosymmetric. So to give you an idea of what that looks like, so if we had R negative 3M, that would be centrosymmetric. It would have an inversion center. Now, if we had the space group P negative 6, and again, negative 6 is it's the same thing as saying P6 bar. Since this is an even roto inversion, it would not have an inversion center. So what gives you inversion centers? What gives you is a mirror plane perpendicular to a rotation on the same axis. So it's the same axis generating both the mirror plane and the rotation. Another one is 3 perpendicular mirror planes. So you have, this can be glide planes as well. And the last thing is an odd roto inversion. So those are the only 3 types of symmetry operations that can give you inversion centers. Now, P1 bar is a one-fold roto inversion, so of course P1 bar is centrosymmetric. So just to show you an example of 3 glide planes generating a inversion center, I'm going to do that one for you right here. So let's say we want to show that PBCA has a inversion center. So we're going to start with our coordinates, X, Y, and Z, and then we're going to do 3 perpendicular glide planes. So first, what we're going to do is if you read this, remember the first axis is the A-axis, so we have a B glide perpendicular to A. Now the second axis is the B-axis, so we have a C glide perpendicular to B. And then the last axis is C, so we have an A glide perpendicular to C. So now when we perform the B glide perpendicular to A, that means the X becomes negative. We add a half to Y and no change in Z. So that's the first. Now when we perform a C glide perpendicular to B, there's no change in X. Since it's perpendicular to B, Y becomes negative. So again, negative a half minus Y and a half minus Y are the same thing. And then we translate 0.5 along Z. And then lastly, we have an A glide perpendicular to C. We get 0.5 minus x, 0.5 minus y, and then 0.5 minus z. So notice here, the key thing to note is when our initial point, x, y, and z, our final point we have negative x, negative y, and negative z. So that means it's an inversion center. The halves, what that means is that it's off the origin. So this inversion center would be at the coordinates 0.25, 0.25, 0.25. So that means this inversion center would be located at this point in the unit cell, a quarter, a quarter, a quarter. So whenever you have glide planes, if you have three perpendicular glide planes, you're going to generate the inversion center, and you know for sure that it's going to be typically on a quarter, quarter, quarter point in the unit cell when you have three glide planes. So just to show you that glide planes do result in inversion centers. So again, a mirror plane perpendicular to a rotational axis, so that means you have rotation and a mirror plane about the same axis. Three perpendicular mirror planes or an odd roto inversion give you centrosymmetric space groups because they generate an inversion center. So one of those operators would be a inversion center. And so here's just more examples. So we have the space groups PNMA and P21 upon C. Now PNMA, it has two glide planes and one mirror plane. So even this combination, since they're all perpendicular to each other, they will generate an inversion center. So again, what you notice is our initial points x, y, and z. Our final points, we get negative x, negative y, negative z. So the coordinates have all become negative. The plus half on each one just means that it's been shifted a half a unit. So again, like we said on the previous example, we have an inversion center at a quarter, quarter, a quarter. Now on the second one, we have this monoclinic space group P21 upon C. So again, starting with our initial coordinates, x, y, and z, we do a 2-1 parallel to B. We get negative x, y plus a half, negative z. And then we do a C glide perpendicular to B. So then we get negative x, y plus a half, negative y plus a half, negative z plus a half. So what you'll notice is the x, y, and z have gone negative. So that means that that's an inversion center. The halves mean that this inversion center is at 0, a quarter, a quarter. And so both of these are centrosymmetric space groups. Now if we look at P21 upon C, we want to do all its symmetry operators. P21 upon C. So again, the first symmetry operator is always the identity x, y, and z. The second operator, and let me just put identity in parentheses, so that's identity. The second operator is a 2-1 parallel to B. So that means negative x, y plus a half, or 0.5 plus y, negative z. And again, this is a 2-1 parallel to B. The third operator would be the C glide perpendicular to B. So C glide perpendicular to B would be x, negative y, z plus a half. And this is a C glide perpendicular to B. And I'll put the perpendicular sign in just a moment. Now, remember, space groups have an even number of operators. So P21 upon C has 4 operators. So the last operator is the inversion center, which is a combination of the 2-1 and the C glide operators. So we get an inversion center at negative x, a half minus y, and a half minus z. So this is the inversion center. So these are the four operators that make up P21 upon C. Now, if you had the space group, for example, C21 upon C, if that did exist, it would have a total of 8 operators because you would have 2 unique lattice points. So this right here would be a glide plane. Now, if we look at P in MA, we'll look at its space groups and then we'll move on. This is just good practice. So we have P in MA. Again, the first operator, we have a identity x, y, and z. We always start with that. Second operator, we have an n-glide perpendicular to A, negative x, 0.5 plus y, 0.5 plus z. So this is an n-glide perpendicular to A. 3, we have a mirror plane perpendicular to B, so be x, negative y, z. So this is a mirror plane perpendicular to B. And then we have an A-glide perpendicular to C. So we have 0.5 plus x, y, negative z. And this is an A-glide perpendicular to C. Now, PNMA, it has 3 perpendicular axes. Three glide planes on perpendicular axes is going to have an inversion center. So since PNMA is centrosymmetric, it's going to have 8 operators. So we only have 4 operators. So how do we generate the other 8 operators? And that's by combining the different symmetry operators. So what I'm going to do is I'm going to combine an n-glide perpendicular to A and an m-glide perpendicular to B and see what operator shows up. So we have, if we take numbers 2 and 3 and combine them, we get negative x, 0.5 minus y, and 0.5 plus z. So again, what I did to generate the 5th operator is I combined numbers 2 and 3. And that generates a 2 sub 1 parallel to C. Now we do the same thing. Let's take numbers 3 and 4 and combine them. So if we take symmetry operators 3 and 4 and combine them, we get 0.5 plus x. Oh, I forgot to put a comma right here. There we go. 0.5 plus x, negative y, negative z. And when you look at this, this is a 2 sub 1 parallel to A. And the way I know it's a screw axis is because there's a translation and then there's 2 coordinates that become negative. So the way I know that 0.5 plus x is translation and 0.5 minus y is not is because the y changed sign. So negative, something minus x, y, or z is not a screw axis. It has to be a positive x plus a half. So this translates along the A, and we change the sign of y and z, so that's a screw axis parallel to A. And then lastly, the last combination is combining numbers 2 and 4. So if we can combine 2 and 4, we get 0.5 minus x, 0.5 plus y, and 0.5 minus z. And this would be a 2 sub 1 parallel to B. Now remember there's 8 operators, so the last operator is when you can do, if you combine numbers 2, 3, and 4, like we did down here, 2, 3, and 4, we get an inversion center, 0.5 minus x, 0.5 minus y, 0.5 minus z. And this is a inversion center. So these are all the operators for PNMA. Again, orthorhombic centrosymmetric space groups are going to have double the number of operators that are when you have non-centrosymmetric space groups. So non-centrosymmetric orthorhombic space groups have 4 operators, but when you introduce that inversion center, you generate double the number of operators. So always, even in monoclinic, centrosymmetric monoclinic space groups will have double the number of operators for their corresponding non-centrosymmetric space groups. Just put these signs in. So now if this was a C-centered, it would have a total of 16 operators. So you'd have all these operators for the primitive form, and then you have to redo all of them for the C-centered form. So generally what they would do is if you look at these up in the table, for C-centered, they would just say, you know, in addition, you would have the lattice points. If this was C-centered, it'd be a half 0. So that would tell you that this is in addition, these would be also for this lattice point as well. But for y'all, you'll have to write them out if I ask you to write them out. I can't do the shortcut. So one more thing I want to show you, just to show you the comparison. So P2, 1 upon C, we said had 4 lattice points. Not 4 symmetry operators, sorry. 4 symmetry operators. And it is centrosymmetric. Now if we compare this to just the space group P21, P21 is non-centrosymmetric, and it only has 2 operators. Likewise, move it down here. Likewise, if we had the space group PC, it's also non-centrosymmetric, and it has 2 operators. So the operators in both of these is the identity and the screw axis for P21, and the identity and the C glide perpendicular to B for PC. So you can think of P21 upon C is the combination of P21 and PC, and when you combine those two space groups, you generate P21 upon C, where you also add in an inversion center. So if you look these up in the handbook, the subgroups of P21 upon C are going to be P21 and PC. And the same goes with orthorhombic, but those can be a little bit hairy, so we're not going to look at those. So again, the key things to finding an inversion center is, does a space group have a mirror plane perpendicular to the rotation axis? So these are all examples of a rotation perpendicular to a mirror plane, or mirror plane perpendicular to a rotational axis. It can include screw axes or even glide planes. Does the space group contain 3 mirror components? And again, these can be mirror planes or glide planes, so they look something like this. And by the way, all of these here are orthorhombic space groups because they all have 3 major axes. Does it have an odd roto inversion? Then it's going to be centrosymmetric, so all of these have an odd roto inversion present. So now when we get to the bottom, let's see if we can go through and determine which ones are going to be centrosymmetric or non-centrosymmetric. So I'm going to circle the ones that are centrosymmetric. So let me give you 1 or 2 minutes to kind of look through these and see if you can identify the centrosymmetric ones, and then I'll go over it with you. Thanks. Yeah, my bad. I think you can hear me now, right? Yeah. Okay. Sorry about that. I turned it off while y'all were working on it. I forgot to unmute. So the ones that I've boxed in, P21 upon M, it has a mirror plane perpendicular to a rotational axis. The ones that I marked off don't meet these 3 requirements. And PBAM, it has 3 perpendicular mirror components, so it's centrosymmetric. A CMMM again has 3 perpendicular mirror components, it's centrosymmetric. I41 upon M is a rotation and a mirror plane perpendicular to that rotational axis, so it's centrosymmetric. P3 bar M, so 3 bar is a odd roto inversion, so it's centrosymmetric. The P4 bar was not centrosymmetric because it's an even roto inversion. Now R32 does not have any roto inversion or mirror planes, so it's going to be non-centrosymmetric. R3M, again, doesn't have 3 perpendicular mirror planes or a odd roto inversion or even a mirror plane perpendicular to a rotational axis, so it's not centrosymmetric. P63MC, this does not have 3 perpendicular mirror planes or does not have a mirror plane perpendicular to a rotational axis or an odd roto inversion, so it's going to be non-centrosymmetric. When we get to the next one, here we have P63 upon MC. So this space group actually meets 2 requirements. It has a mirror plane perpendicular to a rotational axis, which is this right here. In addition to that, it has 3 perpendicular mirror planes. So this one is centrosymmetric. Then we have P6 bar 2C. We don't have 3 perpendicular mirror planes. We don't have an odd roto inversion. And we don't have a mirror component perpendicular to a rotational axis. IA3 bar D, here we have an odd roto inversion, so it's going to be centrosymmetric. P4 bar 3M, we don't have an odd roto inversion. We have an even, but evens don't generate inversion centers. We don't have 3 perpendicular axes, mirror planes, and we don't have a mirror plane perpendicular to a rotational axis. So this is non-centrosymmetric. And then lastly, we have PN3 bar M, and again we have this roto inversion. It would be centrosymmetric. And so that's how you go through and identify what's centrosymmetric and what is non-centrosymmetric. Oh, I highlighted them too. That's good. Okay. So just to quickly talk about point groups, we did touch on this when we were talking about crystal systems. There are 32 crystal point groups that we use, and this is based on the point symmetry. So what we do is, for point symmetry, we reduce screw axes and glide planes down to mirror planes and rotational axes. So point groups do not have any space symmetry in it. So anything that was space symmetry, we reduce down to its point symmetry. And this is good for grouping crystals with different types of properties. So certain point groups are polar, certain point groups have ferroelectric properties, etc. And so just to give you a few examples of this, we have, C2 upon C would be in the point group 2 upon M. So again, you reduce the C glide down to a mirror plane. P21 upon C would be in the point group 2 upon M, because again, you reduce the screw axis to a twofold and you reduce the C to a mirror plane. And of course, C2 would be in the point group 2 for C2. And so there are actually 4 point groups for monoclinic. So monoclinic, I'm just going to do monoclinic to show you, but monoclinic has 4 point groups. It has M, 2, or actually it starts with 2, M, or actually it has 3, excuse me, 2 upon M. So those are the 3 point groups for monoclinic systems. They're either going to have twofold symmetry, a mirror plane, or a twofold with a mirror plane perpendicular to their rotational axis. So now we look at orthorhombic. We have PNMA. It's going to have the point group MMM. PBCA also has the point group MMM. And let me just write that to show you here. If you're in the point group orthorhombic, if you have the point group MMM, what's unique about this point group that you should know? That's right, the point group is centrosymmetric. So if you're in the point group MMM, every space group in that point group is going to be centrosymmetric because you have 3 perpendicular mirror planes. Likewise, for monoclinic, if you're in the point group 2 upon M, this is a point group that is a mirror plane perpendicular to a rotational axis. So this would be a centrosymmetric point group. So any space group that's in this point group would be centrosymmetric. And that's a very good way to help identify if things are centrosymmetric or not, is looking at the point group. So does your point group contain a rotation perpendicular to a axis? Does it have 3 perpendicular mirror planes? Or does it have a roto inversion? Because remember, roto inversions are point symmetries. So if we look here, for example, with trigonal, this negative 3M, that would be a centrosymmetric point group because it has an odd roto inversion in the point group. Whereas for cubic, the point group M negative 3M would be a centrosymmetric point group because it has an odd roto inversion. So another way to determine centrosymmetric or non-centrosymmetric is looking at the point group of the that the space group is in. So this is just showing you a breakdown of the different point groups and the Hermann-Malguin notation and then the Schneeflies notation for point symmetry. So like I said, for monoclinic, we have 3 of them, also for orthorhombic. And while we're here, we'll see if we can go through and identify the centrosymmetric point groups. So of course it's going to be this one, odd roto inversion. We've talked about this one. And then we also mentioned MMM, that's a centrosymmetric point group. Now if we go to tetragonal, we have this one and this one. So the point groups I circled are centrosymmetric point groups. So if you know your space group is in one of these point groups, automatically you know it's a centrosymmetric space group. And so just to explain just a little bit about non-centrosymmetric crystals, they have different types of properties. So depending on the type of space group it's in, it can have properties like it can be enantiomorphic, it can be have optical activity, it can be polar, pyroelectric, or piezoelectric. So non-centrosymmetric crystals are important because they exhibit unique properties as well. And so that's the end of part 1. I'm just going to start on part 2 today, but a lot of what's in part 2 I've already covered in part 1. You'll see it's kind of an overlap because a lot of that going through the different symmetry operators in part 1, we kind of do the same thing in part 2. So I'm just going to start on today for about 10 minutes, and then we'll continue with that on Monday. But what we've gone over so far is more than enough to complete the quiz that's for week 2. So let me just stop to share for just a moment. And we'll bring up the other lecture notes. And this is mainly, breaking down space groups. Let's see. So here we're just going to be utilizing space groups. So we're going to be applying the symmetry in the space group to see if we can generate all the symmetry related elements. And the reason space groups are important is because once we know the symmetry elements, we can generate symmetry related atoms or positions in the unit cell. And so this is important. What you're doing when you're solving a crystal structure is you're solving what's called the asymmetric unit. So we talked about a crystal is a regular repeat unit, which is the unit cell. So the unit cell gets repeated in 3 dimensions due to translation. But within that unit cell, you have to solve what's called the asymmetric unit. And the asymmetric unit is the smallest unique portion of space in the unit cell, which is used to generate all other symmetry related positions in the unit cell. So once you have your asymmetric unit, you have your space group, you can generate all the different molecules or entities in the unit cell. So in this example here, this gray area is the asymmetric unit. So if you were to run a crystal of this compound, what's in the gray area is what you would be solving physically in the program OLEX, for example. Once you solve that, refine it, then you would use symmetry to generate the rest of the molecules. So for this example, these are all the symmetry operators for this particular crystal structure. So this is a very high symmetry system. And so that's what you're solving for when you solve a crystal structure. You're solving for the asymmetric unit. And it doesn't have to be a whole molecule. It can be a half molecule. It could be 2 molecules. It just depends. So it's just an example of an asymmetric unit. And the main thing is to note is that it doesn't need to be an entire molecule. So in this example here, this is the asymmetric unit. So this is what you would solve for when you're solving the crystal structure. Once you determine what the asymmetric unit is, then you can use symmetry to generate the equivalent positions to generate the entire unit cell component. And it's this unit cell component that gets translated in 3 dimensions. So, and just showing you different examples. So here we have an example of a asymmetric unit on the left. So it can be parts of atoms or parts of molecules. It doesn't have to be a whole molecule. And then, here what we're looking for are these, and this is a complete overall structure. So once you have the asymmetric unit, you can generate the rest of the unit cell. All right. And so one thing we're looking for in the coordinates is we want to know if there are coordinates that are on what we call special positions. So there are 2 types of coordinates in crystal structures. We have special positions and we have general positions. So for example, in this set of fractional coordinates here, strontium 1 and iron 2 are on special positions because they're on very clean fractional coordinates. So strontium is at 0, 1, 1/2, and iron 2 is at 0, 1, 0. The rest of them are on what we call general positions because they don't have clean fractional coordinates. And one thing to note is that the asymmetric unit doesn't necessarily have the same number of atoms as the entire formula, because the formula may be generated once you do all the symmetry operations for that particular crystal structure. But in cases that they do match up, that's generally because there's 1 molecule in the asymmetric unit, which is the same as the formula. And we'll talk more about that when we actually solve the crystal structures. So again, we have two types of coordinates. We have special positions and we have general positions. As I said earlier, general positions are messy coordinates. Their numbers don't have clean fractional coordinates. Special positions have symmetry operators that pass through the site. So for example, 0.250 is a special position, probably an inversion center, or 0.473.5. Since the 0 and 0.5 are special, this could be a rotational axis. So 0, y, 0.5 would tell you this is a rotational axis along the y-axis. When you have one special position, that usually indicative of a mirror plane. Two special positions, usually indicative of a rotational axis. Three special positions indicative it may be on a inversion center. So when you're on a special position, usually on your symmetry related position, you generate fewer atoms. And we already talked about that. So, we'll stop here for today. We're in this lecture, and we'll start up on Monday, continue on space groups. So we'll be talking about how do we build the unit cell from the asymmetric unit. So I'm going to go ahead and stop for today.